recording?
Nandini is recording, ma'am.
Okay, fine.
Okay. So as I was mentioning, now we'll be like discussing about these three different model validation techniques, because in machine learning, building a model is very easy. You just have to get to know the crux of algorithms, and then you can just have your data sets, and then you can just like create your model. But finding out whether your model is performing well or not, that's a major thing, because that's where your expertise should be in. Okay, so we'll just like look into the very important validation techniques now. The first one is bias variance trade-off. So to understand the trade-off between these two factors, I think you have to first understand what is a bias and variance. Okay, so bias is nothing but difference between your predicted value and the expected value. So we already have your observed value, your target variable, right? Which is part of your data, and then we will be like predicting the values. If I mean, we are talking about regression algorithms, okay, where you'll be like trying to find a continuous variable as your target variable. So when you find the difference between these two, you will be able to find your bias. Okay, so variance is nothing but when you like find a difference between the predicted value mean and the observed values. I mean, your target variable minus your predicted value mean. Okay, that is your variance. Whereas in bias, you're just like trying to like compare the difference between the predicted value and the expected value. Here you're doing the difference with the same expected value with your mean of predicted value. Okay, that is variance. Okay, so I'm sure you should have like come across this formula. So we always get to know errors in when you build a model. So this bias and variance is part of your error. Okay, so error is nothing but your bias, variance, and some noise, which you cannot find out why you have this kind of noise in your data. Okay, so all these things leads to a error in your model. Okay. Okay, so when this bias occur, and what happens when there is a bias? So when you're training your model, and then if you have a high bias, okay, which means your model will be underfitting, which means your model is not learning properly. Okay, it is not learning properly, so that you will be having a high bias. But if your model is like kind of learning too much, your model will be overfitting. Okay, so here's some example here. So this is how the underfitting model looks like. So actually the data is actually looks like a U-shaped data, right? So the data is scattered in this format, whereas when you see the underfitting model, so this line I mean never correlates with the data, right? And when you see the overfitting, it's like too much overfitting, right? It connects the dots exactly where it has supposed to be. And this is not the right model as well. So the desired model should be like this, where you are able to like form a model with right bias and right variance. So usually your bias and variance should be very low. Okay, so to create a perfect model, because we always want to minimize our errors, right, in the model. So your bias and variance should always be minimized. Okay, so this picture will help you to understand how you should be working on your bias and variance, right? So when you have a low bias and variance, you have your data points like concentrated on the center. Okay, but when you have a high bias but low variance, so your points are like they're like clustered together, but still it is like completely away from the center point. So this is not the right way. And if you have low bias and high variance, so your points are like it's like kind of scattered towards the center, but it's like it's not like glued with each other. It's kind of they're like have a very big difference, I mean distance between each other. And high bias and high variance, I mean this is not the right way that you should have your points. Okay, so the right method, right way of having your low bias and low variance is like having your data points in the center. Okay, So this diagram shows us like how your bias and variance should be. So when the model complexity increases, your bias decreases, but your variance will increase, because it's overfitting. So you always have to find a trade-off between both the bias and variance, so that you find a optimal point. Okay, so at this optimal point, your error also will be minimum. Okay, because we know error is equal to bias plus variance plus noise, right? So when the bias is less, your error will be less. When the variance is less, your error will be less. So you have to find the optimum point where both of this meet, and then you have to like conclude your model with these numbers. Okay. Yeah, so we always talk about this, but how to implement this in Python? Okay, so to identify your bias and variance of your model, you have to use the function bias underscore variance underscore decom. Bias variance decom. With that, you will be able to find your mean square error, bias, and variance. Okay, so this is actually this is for a linear regression model. So that's why you have MSC here. So to get these numbers, you have to use the bias variance decom function. So MSC is nothing but your error, right? So bias plus variance gives you the error. So imagine I don't have any noise in my data. So 21.7 plus 1.76, it actually gives 22.4. So bias plus variance gives you MSC. Okay, mean square error. So I'm sure you all know what is R square and adjusted R square is, and that's how uh, you know with all this number you should be able to find out how good your model is. Okay, so I leave all that to you. We are just like looking only on the model validation techniques. So I guess you got a very fair understanding on bias and variance right now. Okay, so now we will just like move into cross validation. Okay, so usually what we do when we like run a machine learning model, we like get the data, clean it, look for any missing values, and then we do some imputation, and then we do data manipulation. We try to understand the data, and then we try to create a model. So when we try to create a model, we always try to you know uh, split your data into training and test set. Okay, so but some people will be having a validation set as well. So they'll be like splitting the data into training set, validation set, and the test set. So imagine you just have a data of only 150 rows. For example, take iris data set. You just have only 150 rows, right? So like splitting your data into three different things, you might be able to you might be able to lose to build a good model because you don't have enough data. Okay, so to solve these kind of problems, people go for cross validation techniques. Okay, so this is nothing but a technique which is used when you want to like reserve a particular sample of data set when you train your model, but you are not actually using that data to train your model. Okay, so you split your data into training and test set, and then you apply cross validation on the training set. Okay, so when you do that, you will be able to like decrease your bias and variance, so that you don't like you have to deal with overfitting or underfitting. So maybe I can like show you something. Yeah, this will be able to like make you understand what cross validation is. So usually when the data set, we split that into training and test set, and then on this training data we apply cross validation, and then we find out the parameters, and then we apply on this trained model. Okay, I'll just show you how this has been done. There are like a lot of techniques available in cross validation, so we'll not be like looking to each of them. The most popular and reliable methods are like k-fold cross validation and stratified k-fold. These are the two things which are currently used in the industry right now. So we'll be just looking only on these two things, k-fold and stratified k-fold. Okay, so here in k-fold cross validation, what you do is like you split your data into different k-folds, I mean different chunks. Okay, in this diagram you will be able to understand. Imagine you have a data of 150 rows. So take your iris data set. So you will be like splitting your data into 5 training and test data, right? So imagine I got my 50 50 rows of iris into test data, and I have only 100 rows of iris data set in my training data. So I'm splitting that 100 rows into 5 different folds. Okay, so and then I apply training on only the four folds, and then I train the model using the 4 folds of data, and then I test it on the other fold, and then I repeat the same thing. So here I was like, training the data on the fold 2, 3, 4, and 5, and then testing it on fold 1. In the second iteration, I will be like training the data with fold 1, 3, 4, and 5, and test it and validate the model with the fold 2 data. And it goes on. Okay, so here I'm just like, splitting my data into 5 different chunks. So if sometimes if you have a very big data set, and then like you don't have 1 million records, in that case you can even try to have 10 folds, 20 folds, and then this iteration will go on. Okay, based on the folds that you wanted to specify. You can decide how many folds that you want to create. Okay, that's according to the user discretion. Okay, so finally you create a model, and then you'll be, for each of this you will be able to get your parameters, right? And you all these parameters will be like taken average, and that will be used upon your test data. So that's how it works. Okay, so I've just like given an explanation of all this in here. Okay, so that's what I was saying. So you'll be randomly splitting your data into different k folds. So you'll be like building your model on k-1 folds, and then you'll be like checking the model on the validation set. Okay, and you will be like keep on doing this until all the folds get completed. Okay, so you take an average of all this errors, and then you call that as a cross validation error. Okay, so for example, if you're doing it for a linear regression, this thing, so you'll be like able to find MSE for this first run and second run, and then for all this you'll be getting a MSE values, right? And then you'll take an average MSE score, and then you'll be like getting that as your training error. Okay. Next is a method of stratified k-fold cross validation. It's also, it's similar to k-fold, but here you'll be having a chunks which actually are representative of your whole data. Okay, the same process is repeated, but the way you get your folds is different. For example, imagine your data has 30 females and 100 males of 130 records. So even your chunks will have the same distribution. So for example, it's like imagine just 30-70 ratio. So all your folds will be having a 30-70 ratio of your gender variable. Okay, so you have to choose either stratified k-fold or k-fold based on your requirement. If you want to have your all your variables to have good importance in each of the folds, you can go for stratified k-fold. Otherwise, you can just like go with k-fold. So these are the major things, major types of cross validation techniques used in the industry currently. Okay. So I think you got what I said. So I'm just like going to give you a snippet of the code here. So here you just have to like import k-fold for k-fold CV, and then for stratified k-fold is stratified k-fold. Okay, it's very easy. You just have to mention your repeated k-fold, and then I mean you have to mention repeated k-fold when you want to repeat the iteration again and again. So I want to like split this data into 5 splits, but I want to like have an iteration of 10 times of the same thing. So if you don't want to have repeats, yes, it's fine. If you want to like decrease your training error, yes, you can do that. Okay. So for stratified k-fold, you can use stratified k-fold. Okay, this is your syntax. So hope you are able to understand this couple of cross validation techniques. Next is subset selection methods. Okay, so here imagine you have a data set with 150 features. You may not be able to like use all the features in your model. because some might be like completely irrelevant, right? So to identify the right features that you should be using in your model, we have to use the subset method. Okay, so first you identify all your features, and then you create a subset. Okay, what are the features that I'll be using, and then you apply your algorithm on top of it, and then you get to know the results, right? Okay, my R square value is not good with these features. I think I have to like redo my features. So you go ahead and then check on your subset, and then redo your features, and then do the same. You do this iteration again and again until you get the best numbers in your model, and then get this into production. So that's how it works. This is a process. So again, here we have a lot of methods in the subset selection. We'll be like looking into the important types right now. Okay, the first type is a forward selection method. So here, what you just you'll be like starting with very scratch. Here you'll not have any variables in your model, so you keep on adding one variables one by one in your model. Okay, so in this case, you just add one variable into the model, and then you look into your R square value. Okay, I think it's very less. I think I have to add the next variable. So you keep on adding one by one. Okay, you do this until you get the right R square value, or you happen to like add all your variables, or sometimes you might think, okay, I can add only 10 variables. That's no limit here. So in that case, if you're able to like add all your maximum number of variables, yes, you can do that. So you can stop this. So here you'll be like starting your model with no variables, and then you'll start adding one by one. Okay, in the backward elimination, it's completely opposite of your forward selection. So here you will be having all your variables in the model, and then at each step you will be like removing the worst variable, the variable which has a very less which has a high p value. Maybe you can just like try to eliminate it, and then run the model to check on your R square value. If you're like kind of happy with what you get, I think you can stop at that point. So this kind of a small example here. So imagine here I have the p value. So you see here for this variable, the p value is around 0.8, right? So maybe I can try to like remove this variable in the backward elimination, and then I will be like looking to my R square, and then it might increase, right? So after this, maybe I can just try to remove this obese variable. It's 0.7, so it's having a high p value, right? So based on this, you can do that. Okay, this is an example of back backward elimination, right? And then okay. So sometimes people use combination of both of these methods. So here they'll be like adding the best attribute and remove the worst one, and they do it together. Yes, that is also possible. And next one is the recursive feature elimination. This is actually kind of a little complex approach, and it's kind of used majorly in the industry. So here it actually does a greedy search to find out the best feature. Okay, I mean it's not like find out the best feature. It actually finds out you the best performing feature subset. For example, I might have best features as like feature 1 and feature 2, but when they combine together, they may not give me a good number. But when feature 1 might be combined with feature 3, I'll be able to like get a good R square value. Right. So this method actually it creates different models with different subsets iteratively. And try to identify what is the best feature with F1, what is the worst feature with F1, and what is the best feature with F2, what is the worst feature with F2. So it checks out all those combinations. So sometimes you might like end up getting too many combinations. For example, if you have 5 variables in your data set, you might end up getting 2 power 5 different combinations. Okay, so it's time consuming, yes, but still if you have a very big data, it is time consuming, but you'll be able to get a very good subset with this method. Okay, it actually ranks your features based on the order of elimination. Okay, so for each of the feature will be like given an order. So the features with the less best rank can be like eliminated. A sample code for your recursive feature elimination is here. So you have to like import RFE from your feature selection. Okay, and then you just have to like here I just like mentioned logistic regression. So for this model, so you have to like RFE, and then you mention, okay, I just want to select only 3 features. Okay, so it selects only the 3 best features which can go together. So for example, if you want to have a features 5 features in your subset, if you want, yes, you can just like take 5 best features. Okay, yeah, that's all. I think you got an understanding of this. If you got any questions, you can ask now.
Ma'am, for future subset selection, we can use embedded method. Ma'am.